arrived recently. I'm Lawrence Krauss. I'm Director of the Origins Initiative here at ASU. And it's my great pleasure in a minute to introduce my friend and colleague, Brian Greene. Brian needs little introduction. He's probably known to many of you. He's not only a distinguished theoretical physicist and one of the people driving a very exciting area of physics called string theory, but he's one of the most successful and well-known popularizers of physics, or in fact of science, in this country and around the world. Now, what we've decided to do is something a little bit different. Because many of you may have seen his television show or read his books, what we thought, in order to provide, in some sense, a break from the continuous lecture format, is we're going to have a dialogue, and we're going to talk together about some of the issues of physics and science education and communication, and then we'll open up to questions from the audience. So I'm very proud and pleased to welcome Brian Greene to the stage here today. Brian. Thanks, Brian. This will be an interesting experiment to see how it goes. I thought we'd begin by asking, in some sense, what made you become a physicist? What got you excited? And why did you choose the area of physics that you ultimately decided to work in?
You know, I've never thought about that before. No, it's a great question. I think, like many of us, and it's probably true for you too, and I've never spoken to our community, but I started in mathematics. You know, as a little kid, my dad would set me these little problems, and I was just amazed at how, with just a few little tools of knowledge, you could actually calculate things, you know, multiply numbers and do calculations that perhaps no one had done before. No one had done before because they weren't interesting, but it was still, you know, fun for a kid to do. And then later on, I must have been 12 or 13 or 14, you know, I went through the kind of thing that most everyone goes through. Why am I here? What's it all about? All that kind of, those interesting questions, those deep questions. And it just occurred to me that if people are still asking those questions, there must not really be some fundamental answer. So maybe the best you could do is try to understand the question. And when I learned that math could help you learn about those questions, you know, how the universe began, even what it means to ask that question, I was pretty hooked.
So that's interesting. You came in from math. I think that's...
Yeah.
What about your parents? Were they surprised, disappointed? My mother wanted me to be a doctor, for example, and she was very disappointed when I became a physicist.
Are you Jewish?
Yeah.
Yeah, me too.
Yeah.
So, yeah, I've had exactly the same experience. In fact, I still have that experience.
Yeah, well, I got a job at Harvard. My mother said, I remember my first job at Harvard was a nice job, and my mother said, it's still not too late.
Yeah, absolutely. No, my dad was a composer.
Oh, okay.
And as with many composers, very hard to make a living. So he supported the family by playing bass fiddle at weddings and bar mitzvahs and things like that.
Really?
And he was a vocal coach as well, a singer. My mom was a secretary for a veterinarian, so it was not a very traditionally academic household.
What about, I know one of the reasons I write books, and I wonder if it's a reason for you. What about, did you read books by scientists? For me, that was very inspirational. Did that affect you at all?
It did, a little bit later on. You know, I somehow didn't know about this whole area of science books without the technical details until I was at least sort of 13 or 14. Huh. But it was really two books. It was a Carl Sagan, you know, Cosmos, but it was also The Ascent of Man,
yeah,
Bronowski. And those two really just stuck with me as a very potent way of communicating information without having to go to a course, without having to study it. And so that certainly was with me all through my education as something I valued.
Okay, so why then physics and not mathematics, although?
Well, it was really just a recognition that math, you set yourself the problems, whereas in physics, nature sets you the problems. So it felt like you had the capacity to, in the most grandiose language, sort of touch eternity. You know, if you were lucky, if you were among the lucky few whose work actually was relevant to the world, you'd be revealing something that could stand the test of time. And that, to me, just had this pull.
Okay, now we got to physics, particle physics, and ultimately string theory. What about that?
Well, when I was in college, I had a real obsession with gravity. And I'm hesitating.
I think that's true of pretty well all students, actually.
Yeah.
So-
Well, I'm hesitating a little bit because it was a little bit odd. I mean, many of you may be familiar too, but you know well Steven Weinberg's book,
Yeah.
Gravitation and
where I learned
Cosmology,
it.
Principles and Applications of General Theory of Relativity. And, it's this, and I bought that book. I didn't understand it at all. I think it was like a freshman or sophomore, but I used to walk around with carrying
Did
it,
it help you meet women? Or
caressing it, sort of. I just wanted to know what was inside that book. And then when I began to understand it a little bit and learn that there was this big issue, how do you incorporate quantum physics into gravity, I became very, very caught up with that notion and basically stayed in that area ever since.
Now, I'm trying to remember, because I think I was at Harvard when you were still a student there. But when string theory already, I mean, you were interested in gravity, but string theory hadn't yet taken off.
It was an interesting timing. So I graduated in '84 and went to Oxford. And in the fall of that year, fall of '84 was really the big breakthrough year. So at Oxford, there was this sense at first, when I first got there, I have to say, the older students said, turn back.
Yeah, quantum gravity, before string theory, it was the dead end. All these good students want to do it, and you never heard their name again.
And moreover, there were even particle physics students who said, this field is drying up. And it was a real kind of depressing couple of months hearing the older students with that perspective. But then, this big shot out of the blue, these discoveries in string theory just changed everything.
Yeah, maybe now it's time to talk a little science. So maybe want to fill in a little bit about what happened. What was the major breakthrough that made string theory of interest to people, and then
sure.
we can go on.
I mean, maybe 30 seconds background on string theory itself.
Yeah.
So, as many of you may be familiar.
Well, I think
I guess the audience already knows all the string theory.
Yeah, that's right.
I forgot where I was.
Yeah, that's right. This ASU. Now, come on.
Yeah.
Okay.
Anybody want a little bit of background string?
Yeah.
Okay, good. So, in the 20th century, the two big developments that we all study intently were Einstein's breakthrough in understanding gravity, the general theory of relativity, and the other breakthrough in a field called quantum physics that focuses on the completely other realm of the spectrum in terms of size, the small things. General relativity big, quantum mechanics small. The weird thing was when you tried to put them together, the math just wouldn't work. So this was a big puzzle. And string theory is an approach that tries to resolve that puzzle, put gravity and quantum mechanics together into one theoretical package. And the only feature of the theory that really I think is worth keeping in mind, because it's very visual, string theory suggests a new way of thinking about the ultimate constituents of matter. Molecules, atoms, subatomic particles, we view them as little tiny dots traditionally. String theory suggests, and I underscore suggests, these are not proven ideas, but inside of these little dots, string theory suggests you'd find something else, a little tiny filament, a little tiny string-like entity that vibrates. And it's called string theory. It looks like a little piece of string. And the idea is that the different vibrational patterns of this little tiny filament is what gives rise to the different particles. The string vibrates one way, it looks like a quark. It vibrates a different way, it looks like a photon. So all the particles are the different musical notes, if you don't mind that metaphor, that the little tiny strings can play. That's the basic idea.
And there's another important component of it, a very important component of it, is that string theory to be mathematically consistent requires extra dimensions. Maybe it's very important. The strings vibrate not just in the dimensions we see, but in principle, extra dimensions, which is a major challenge of string theory because most of us in the room usually are used to just 4 or 3, in fact, and we rarely throw a baseball and have it disappear into an extra dimension. So maybe you want to talk about that a little bit.
That's absolutely right. That is one of the strangest implications of the theory. So when I said that you put general relativity and quantum mechanics together in one mathematical package, what I really should have said is there's a mathematical framework that when you study it, you find that it fails if there are only 3 dimensions of space. That is, if you only have left, right, back, forth, and up, down, these 3 dimensions that we all know about, the math breaks. And some people said, well, let's look at it even more intently. What happens if there are 4 dimensions of space? It still breaks. 5, 6, 7, 8 still breaks, but you get to a total of 10 space-time dimensions, and all of a sudden the math falls into place. So that's where this strange idea that there may be more dimensions of space than the ones that we know about comes from. And frankly, I and many others have spent the most of my career trying to figure out where those extra dimensions are, what their features look like, and perhaps what implications they might have for physics that we can see in the world around us.
Now, in fact, of course, one of the big it's interesting, when this idea first came up, the idea of extra dimensions, early in the century, in the last century, it was developed independently by a mathematician and a physicist. And the mathematician said, well, you can have these consistent extra dimensions that do interesting things. But the physicist rightly said, okay, if they are there, how come we don't see them? Yep. And the original idea was that they were extremely small. So they're so small you can't see them. Maybe you want to elaborate on that.
Sure. So the gentleman you're referring to, Krauss, way back in 1919, was basically studying Einstein's general theory of relativity, which had been so successful at describing the force of gravity. And the language that Einstein used was unfamiliar. He used the language of curved space, in fact, curved space-time, as the medium for mediating the force of gravity. So right now, according to Einstein, I'm sort of feeling myself being pulled down because my body wants to slide down an indentation in the curved space-time that the Earth creates. So it's an unfamiliar idea, but a powerful one. Kaluza looked at it and said, well, that's interesting. What if the other forces of nature, namely the electromagnetic force, also can be described in that language of curved space? But the problem was Einstein had used up all of the known dimensions of space. So Kaluza said maybe there's another dimension of space, and maybe ripples and curves in that would describe the electromagnetic force. And he did the math, and lo and behold, the equation for electricity and magnetism popped out by the simple assumption of one more dimension of space. But then the question is, where is it?
And I think it is interesting, don't you think, though, that it's sort of an interesting differentiation between mathematics and physics. That he was just perfectly happy with that and didn't bother to ask the next question. And it was Klein, the physicist, who then asked it.
And it was Einstein too.
Yeah,
that's
true.
So I mean, at least as the story goes, Kaluza sends that paper to
right.
Einstein, and Einstein at first is very excited about this because he himself was fixated on unifying the description of all forces, not just gravity. So he loved this idea that by having one more dimension of space, you could put together electricity, magnetism, and gravity in one framework. Wow, that was just what he was looking for. But then, like you say, he said, hold on, this is crazy. We only have 3 dimensions of space, so this can't possibly be the right way to go. He thinks about it for another year or two, holding up publication of this paper, much to the consternation of Kaluza.
Yeah.
And finally, Einstein says, yeah, maybe this is possible. But it was Oscar Klein who really then came along and said, well, here's how to think about it. There can be more dimensions of space as long as they're really small. The ones we know about are big. We can really see all these dimensions because they're large. But imagine there's a tiny, curled up, crumpled up dimension that's so small that we don't see it. And in this particular case, they imagine if you had a little tiny additional circular dimension all around us. The image that I like to use is, imagine you're looking at a carpet from far away. It looks flat. But then you put your eye right down on it, and you see these little tiny loops, these little pieces of thread called the pile, I guess. So you see these little tiny circular pieces attached to the carpet, extra dimensions, curled up. You don't see them from far away. The idea was maybe that's true of our universe. Extra curled up dimensions all around us, so small that we don't see them.
Okay, so that explains why we don't see them. But of course, there it is over there.
Thank you.
The job of physics is not to explain why we don't see things, of course, but to test the ideas and explain how we can see them, or at least how we can tell that they might exist. Well, maybe you should talk a little bit about the challenge. And one of the reasons that string theory is at this point has not yet sort of made touch with experiments. So maybe you should talk about that a little bit.
Yes, and I think jumping off from the historical line is not a bad way to go, because after Kaluza and Klein suggested this idea of an extra dimension, They did try to see
Yeah.
if it could make contact with experiment, and they found that, for instance, it was very hard, almost impossible, to get the electron, a known particle of matter. They couldn't incorporate it successfully into the theory. And that was largely why this idea was ultimately dropped by the 1940s. Then string theory came along in the 80s, and it didn't just allow for extra dimensions, it required extra dimensions.
Actually, I think it is interesting to point out that it really came along the sort of, or at least the
60s,
in the
yep.
60s,
Yep.
where it was first used to try and explain another
Good
force
point.
of
Yep.
nature. And actually, and maybe it's an interesting question. Neither you or I were practicing physicists then, but at that time, I don't think you were anyway. At that time,
Oh, speak for yourself.
Yeah, yeah, that's right. At that time, it wasn't 10 dimensions; it was 26.
Yeah.
And I was amazed when I sort of gone back and looked at that stuff to think that that the questions were so desperate that people would be willing to accept not 6 or 7 extra dimensions, but 22 extra dimensions. And maybe you want to talk a little bit about why it would be that physicists would sort of be willing to make that incredible leap.
Yes, so you're right. The earliest version of string theory, I should say, did require 22 extra dimensions for this total of 26 if you include time. And I think the reason people were willing to take it seriously is twofold. One, there had been so many attempts to put gravity and quantum mechanics together, and they all failed. They all just broke down. So when an approach came along which seemed to work but required something weird, and yet that weirdness was something that had already been contemplated in one form or another decades earlier, in some sense people said, well, you know, whether it's 1 extra dimension or 2 or 5 or 22, it's the idea, getting over the notion that this is all that there is. Once you allow for more dimensions, the actual number doesn't seem to really sway you much one way or another.
Yeah, I mean, if you got a bunch of X. But I was actually thinking of going back. I think
Yep.
it's interesting to me that even in the 1960s, where they weren't talking about gravity, they were talking about another force which wasn't so profound at that time.
Yep.
There was just a big problem. Accelerators kept coming up with new particles, and there were particles everywhere, and the zoo was growing, and it appeared there was no order. That when people came up with an idea that they thought might provide order, they were willing to at least explore this idea.
That's exactly right.
And I think it represents the fact that it's not, and we'll ask you about, one of the things I want to ask you is if you really think there are those extra dimensions in a moment, but the idea of exploring them and using that hypothesis and seeing where it goes without becoming religiously devoted to it, I think is interesting, is that you're willing to try anything to see if it works. And in the case of the 1980s, what they discovered, well, they'd had the right solution but asked the wrong question. At least they hoped they had. So
that's exactly right. So the earlier version of string theory was not trying to resolve this incompatibility between quantum mechanics and gravity. Strangely enough, the earlier version of string theory, as you say, was trying to describe data that was coming out of accelerators worldwide that were finding this whole slew of particles, the zoo that you mentioned a moment ago, this whole slew of particles without any order. And string theory in its earlier version seemed to supply an order. All these particles now being thought of as different vibrations of the string gave an organizing principle for thinking about this wealth of data. The problem was there was one pesky particle that came out of the mathematics of string theory that was not found in the accelerators. It was a particle that people a few years later recognized as just the kind of particle that you would need if this was a theory embracing gravity, a particle known as a graviton. So people said, let's take a big step back, reevaluate this theory, not just think of it as a theory that describes the particles, and footnote, another theory had come along which did a better job at that, quantum chromodynamics.
And two of the people who won the Nobel Prize for it are at this at our meeting right now, in fact.
So people said, let's not try to answer that question, which that other theory does better anyway. Let's take this vice of this graviton particle, make it a virtue. Think of this now as a theory uniting gravity and quantum mechanics.
Actually, it's interesting you talked about this vice and virtue. It may not be a secret to many of you that Brian and I have appeared on stage a number of times in a more combative format, a debating string theory, which we're not going to do today because I won the other ones. I want you'll get your shot. No, but anyway, why don't you talk about this vice to virtue thing? I mean, in some sense, the difference between the string theory of the 60s and the 80s and since that time is a huge leap. That string theory, in its modern form of trying to attack this fundamental problem of quantum mechanics and gravity, and let me make it clear, I'll say it in public, it's the best bet at this point. Okay, I'll come back to other things about it, but
technical crew, can you just cut out that snippet and send it to me? Just that little piece right there.
No, we're in a complete agreement. But it's completely different in the sense that it's really right now guided by mathematics for the most part. Yeah. And so I wonder whether you want to comment on this sort of role of aesthetics and mathematics versus experiment, because it's a new leap in a sense. So
it is a new leap in some ways, but I think you would agree that if we look back at the history of physics, say in the 20th century, there are many moments where mathematics was playing a pivotal role in guiding the next step. Now, what was certainly the case, for instance, in quantum mechanics, it was much more an interplay between data and mathematics because we were describing a realm that we could probe experimentally. Yeah. So we had the shining light of experimental data to help guide the math, this wonderful back and forth between the theory and the experiment. You know, Einstein, though, was largely guided by just his powerful intuition and mathematics. I mean, the idea that gravity is associated with curved space-time, I don't know about you, but I've never gotten over the awe that I initially felt that he came up with this idea. It's just how in the world did he come up with this? And it was just this powerful intuition that was working within the confines of mathematics.
Although I mean, he did have pictorial experiments. He did have those Goduncan experiments, the idea that light, think of an elevator accelerating. He tended to think pictorially, and ultimately he forced himself to learn the mathematics he needed and was almost beaten by a mathematician at his own game.
That's right. But I think it's pretty clear that it was not just this unbridled pictorial sense, this unbridled creativity. It was working within the context of a mathematical framework that really allowed him to go forward. And I think the difference today is we're in realms that are beyond current abilities to probe experimentally, or maybe not. We'll see at the Large Hadron Collider. There's a possibility. So we have to be guided yet further by mathematics. And could mathematics completely lead us astray? Yes, it's certainly possible. I don't think so, but it's possible.
Why don't you think so?
Well, it's just the experience that we've had. And it's also this deep-seated sense that mathematics is this language. It's almost tailor-made to describing the universe. I mean, we have, as you say, I don't know if they're in the audience right now, but they'll be in the program later on. There are folks in our community who've been rightly lauded because they came up with theoretical ideas, took them seriously, that yielded predictions for particles that had never before been seen, and then people looked for those particles and found them. I mean, it's kind of breathtaking that you do this calculation and these symbols on a piece of paper that you got to by following some well-defined rules, a language, if you will, yields a new insight, and it's confirmed.
In fact, maybe that's something we should spend a minute on, because it actually in some ways relates to the talks we heard earlier and came up at our meeting. It's more than breathtaking. It's actually humbling and intimidating. The notion, I know Steve Weinberg, who was here earlier, has said that the idea that when you're sitting in your room working on a piece of paper, that nature actually obeys the laws, that nature, not listens, but obeys what you're writing down. It is almost incomprehensible when you're actually working on it. It's thrilling but intimidating at the same time. And I think one often sees, it's surprising to me that physicists are seem to be more willing to sort of throw caution to the wind in that regard. We talked about the fact that, for example, one of the reasons evolution isn't more lauded than it should be. Evolution is one of the most remarkable scientific ideas that's ever come up, and certainly Darwin. Einstein's gotten great press, but Darwin did more, actually, in my opinion. But one of the things is that he didn't actually make predictions. It's interesting. He didn't say, hey, there's gaps in the fossil record. We should look there, and it's a test idea. When you find it, you could vindicate it. But in physics, we tend to say, hey, this theory will fall apart if you don't find X or Y.
Yes.
But at the same time, well, let's ask, what would fall apart? I mean, this is the problem with string theory in some sense. right now we don't have something that would fall apart if you didn't find X or Y.
That's right. And framing it that way and using evolution as a backdrop, I think, is quite reasonable because, in a way, we're not using the right language, right? I mean, for evolution, as people were describing earlier, you know, this notion of it just being a theory is sometimes used as a strange and really unjustifiable weapon against the theory because when we, as scientists, use the word theory, we mean something very specific. Yeah. You know, the best available explanation for the data that we have at hand, and we're most happy with a theory when it makes predictions that are confirmed or confirmable. And string theory does not meet those criteria. So in more precise language, you know, string theory should be string hypothesis. You know, David Gross discussed it as a string framework. I use the language string hypothesis.
No, I agree. Know? I think I've always said it's unfair to evolution for string theory to be called theory.
And then I'd have to agree with you, actually.
Yeah.
I'd have to agree with you.
Could we get that?
You know, but there's, you know, it's just historical precedent that this is the language that we've fallen into. But back to your question in particular, we understand a lot about, let me just use the language, string theory, and we have, in my opinion, achieved things in that structure that when, for instance, I was a graduate student starting to work on this, I never thought that we'd get this far in the length of time that we have been working on it. But we've not yet gotten to the point where we can start with the equations and come up with some definitive prediction such that if it is not confirmed, we give the theory up. I mean, vaguely we can come up with things like that, but they're so universal that it wouldn't really rule out string theory. It would almost rule out all of physics if it weren't found. And that's not a happy place to be. And, you know, it's funny how, you know, not with you, but I have encountered some people who almost interpret that as a situation that string theorists are happy with because it's some kind of, I don't know, job security or something like that. You know, people don't understand the tenure system or something like that. But the bottom line is, I certainly feel, and I'm sure all my colleagues agree, that if string theory is wrong, I really want to know right now. I'd like to know 10 years ago. Because I'm not in this game to prove one particular theory right or wrong. I'm in the game because I hope that I'm part of a generation that takes us one step further, regardless of what that step happens to be. So we're working very hard to try to come up with things that we might test. And there are some circumstantial things that we could talk about that might happen at the Large Hadron Collider.
We'll get there probably.
But you know, we cannot do what you asked, namely say, this falls apart unless you find that.
Now, in fact, actually, you know, you hit an important point. People tend to think scientists are wedded to theories. And in fact, scientists most often want to be wrong. More importantly, they want their colleagues to be wrong. And and because it gives you a chance to discover something new. And so in a sense, we want to be surprised by nature. And in fact, it's fair to say that you know, there's an interplay between theory and experiment, and we've tried to talk about that a little bit. And sometimes one leads the other. And if string theory has any validity, it'd certainly be an example of that. Usually, it's the other way around. Usually, experiment surprises us and derives us. And so the other thing I wanted you to elaborate on is that there's a problem that right now we haven't yet made contact with reality. But there also is the mathematics of string theory have gotten, you could either say, more complex or more fascinating. And in fact, if the theory has become much different, in fact, strings may not be the most, it may be not only may theory may not be the right word, strings may not be the right word. Maybe you want to talk a little bit about that.
Yeah, so one of the big breakthroughs in the theoretical development of string theory happened in the mid-1990s, where techniques were developed to go beyond the approximate methods that had almost universally been used in calculations up to that point. And when people employed these more exact techniques, they were able to reveal aspects of the theory that were completely hidden previously. And one of the things that was revealed is that the description I gave in terms of the fundamental ingredients being these filaments, these string-like entities, is incomplete. The theory seems to also have within it objects that are two-dimensional, looking more like membranes, or three-dimensional. We call them three-branes, generalization of membrane, four-dimensional entities, and so forth. So there's kind of a democracy, if you will, of higher dimensional shapes that play a role in the theory. Strings were discovered first because they're the easiest part mathematically to reveal, but if we had the exact techniques from the get-go, we probably would not have singled out strings as the one entity by which we named the structure. So yes, that's one of the big developments, and that has suggested a whole nother way of thinking about the theory.
Yeah, it may provide a slight hope of an observational signature, as we'll get to in a second.
Yes.
But before we get to the possibilities, what do you say to people, not me, of course, but what would you say to people who would say that string theory has fallen on hard times? Whoever. Someone asked me to ask that question.
You know, it's a great question, especially because no doubt some people here are aware that some books were written not too long ago which tried to make a case of that particular sort. And what I would strongly emphasize is that the bread and butter of science and the exciting part about physics is you go forward into the unknown, and sometimes there are very fertile periods when there are huge numbers of breakthroughs and your understanding is just leaping forward. There are other times when the theory surprises you in ways that make you step back and really reevaluate and think about things. Now, a theory falls on hard times when neither of those two things are happening, when it stagnates.
Yeah.
And we are nowhere near stagnation. We are in a period where we are reevaluating and trying to take all of the things that have been discovered and find how to best organize them so that we can gain the deepest understanding of this theory. But because there is this progress, this steady progress, we feel the theory is quite healthy, but perhaps going in directions that were unanticipated. If you view it in that light, I think the theory is not fallen on hard times per se. If you view it, has the theory achieved the goals that it has set for itself? No, not yet.
Not yet. I mean, that was part of the problem. There were some pretty lofty goals set in the 1980s that made it seem as if by the time, you know, you had gray hair, and I was losing mine, just to make that the theory would be solved, that we'd know everything. I mean, there were claims made in the 1980s.
The important thing to know is, as you know, those were not malicious claims, nor were they claims coming from some sense of trying to hype. Yeah. It was really coming from a place of excitement. Excitement, I think. You know, again, you know, during that period, it was so wonderfully exciting. In the 1980s, early 90s, there was this real sense that this is going to take us the final step to the deepest understanding. And look, the well-seasoned researchers knew at that point, calm down, everybody. Yeah. You know, this may be an interesting development, but it's bound to be hard to get it to conclusion.
One of the ways one can, and I don't know the answer to this particular question, one of the ways you can try and judge you know, how a theory is doing is where students are going. And in fact, on stage once, when we were having a debate, one of my colleagues bemoaned the fact that the good students were going to string theory. And you pointed out rightly, I think, that students vote with their feet. And what's exciting is what students go into. And so it was a good sign that the good students were going to string theory. Is that changing at all? I mean, are there more students doing other things that are harder to get students to work on string theory at all?
No, certainly. I mean, my experience is no. But I have certainly encountered students, and maybe it's because my particular research focus of late has been more at the interface of string theory and cosmology. I tend now to attract students that want to work in that domain, that are not working on pure string theory per se, but trying to use the theory to gain some contact with observational data. But I think that in terms, if you were to do a survey, I think that it's quite similar to what it was years ago in terms of, you know, the most theoretically oriented students see this as an opportunity to make the biggest possible contribution, which of course means the biggest possible risk. That's how science works.
It's risk. Now, I don't want to belabor this, the last question in this regard, but what, if anything, would cause you to stop working on this and work in a new direction?
You know, if you started to work on it, you know,
that's right.
Just, you know, something must be wrong.
Well, it's, when it snows in Phoenix, I guess. But
what would stop me from working on it? I guess
I'm still working at cosmology, but anyway, it doesn't matter. Okay.
Which I'm thrilled by. If, for instance, two things I can imagine, and this is quite possible. Somebody comes along, maybe it's some new student, looks at the theory and says, you guys have missed a fundamental inconsistency, a fundamental mathematical flaw that is absolutely insurmountable. That would be enough to say, okay, we have to let this go. And I should say, that has almost happened periodically in the history of the subject, but people then looked harder and the math actually worked when you...
And by the way, I should say, that's the kind of confidence, that's interesting, because that's the kind of thing that drives you further when you think something's going to be wrong and you find out, boy, the mathematics solves things. As a theoretical physicist, that does give you more confidence that there's something right about the theory.
Yeah, absolutely. I mean, there was this anomaly having to do with Yang-Mills degrees of freedom, that trace f squared had to be equal to trace r squared, which came to a total. I just want to see if they can type this out.
I see.
Okay, you can. Yeah, that's close. Yeah, that's not bad. It's falling off a little bit here. Yeah.
Actually, I think
now are we going to get into like some endless loop right here if I actually read what's on
it is. We are.
So
I'm going to.
Yeah. Okay. Yes. Yeah. Okay.
Actually, string loops, but
yeah,
actually, I think the way he wrote the equation down was right. I think he may have discovered something.
There it is. Yeah.
But
the second thing, back to your question, is if a better theory came along. I mean, what we are constantly doing is we are looking at the landscape of possibilities, and if somebody came along with a newer idea that we're like, wow, that maybe retains some of what we've done in string theory, but takes it to a place that gets rid of a lot of the problems that we were encountering, but that's the kind of thing that would make you drastically shift your focus.
Okay, now, I hate when people ask me this question, but I'm going to frame it because the question is sort of where do you think people often ask where's the next great breakthrough, and I always say if I knew I'd be working on it. So let me just not put it that way. But where do you think the most fruitful direction in string theory is right now that may have the greatest payoff?
Well, I do think that the connection to cosmology has great potential. I mean, if you're going to test this theory, there are two ways. Either you test it in an accelerator, you slam things together, and we can talk about what might happen, or you test it through astronomical observations, making use of the fact that the universe itself, we like to say, is itself a giant particle accelerator because the early universe was very energetic, very hot. Things happened there that might be sensitive to the exotic physics that we're talking about. So potentially the imprint of that exotic physics might still be with us in astronomical data. So that's where my focus has been for a number of years. And look, we've done some calculations that suggest maybe in the microwave background radiation there could be a signal. When we first did the work, it seemed quite exciting to me. As we looked further, it began to feel a little bit fine-tuned and less an absolute consequence of string theory. So who knows, maybe they'll find something, but again, if they don't, it won't rule the theory out. So it doesn't quite reach the level that we want.
But I should say that when I came in, started being a research physicist just a few years earlier than you, it was a similar idea. That's one of the reasons I got involved in cosmology. At the time, it was something called grand unification. The unification of the non-gravitational forces required a great leap, not quite as great a leap as string theory, but still a very great leap from where the experiments were. And it seemed to me that the universe, and that's what makes the universe exciting, one of the things is that because it's growing, at early times it was smaller, hotter, much more energetic. And so at early times, there were energies that you could never achieve on Earth in a terrestrial accelerator that were there. And so the universe is a big particle physics device in a sense. And that's really what got me interested in cosmology early on too.
Sure, if you don't mind, another analogy just to amplify that idea, because I think it's a very potent one. If you have a balloon with no air inside of it, and you have a really fine tip pen, you write a little message on the surface of a balloon, it'll be too small for you to see. But then if I blow air into the balloon, it stretches out my little scribble into something that perhaps you can clearly read. So the idea is that the early universe might be affected by these little tiny strings, if string theory is correct, or even the physics of grand unification in some way. And that little imprint of the exotic physics is too small to be seen, and there was presumably nobody there to see it anyway. But then through 14 billion years of cosmic expansion, the message of string theory, if you will, gets smeared out across the sky like my little scribble on the balloon gets smeared out across the expanding surface. So if you know what to look for, or so this approach suggests, you could see the imprints of exotic physics out there in astronomical data.
And let me say, I mean, while that may or may not be the case, that tradition has worked, and probably I'll show some pictures later today, but we use that. One of the reasons that actually one of the people who recently won the Nobel Prize for discovering small hot spots and cold spots in the microwave background is that we definitely think they do provide a signature of another process that happened very early in the history of the universe. And you'll see pictures of it. So it's a tradition that's a noble one, and whether we'll get to the level you want, no one knows at this point.
Right.
But let's talk about that. We mentioned it a few times, the inklings of potentially being able to detect some of this stuff. It's because of, I think, and you'll correct me, I'm sure if I'm wrong, that the discovery of brains in some sense has driven to an interesting idea that maybe originally the whole idea of string theory was these extra dimensions were very, very small, and that's the reason you couldn't see them. But another interesting possibility has arisen, and that is that they might not be so small, and they could be invisible because only gravity can detect them, and gravity is very weak. But the fact that they can be larger leads to something interesting. So why don't you go on to that?
Yes, so you're absolutely right. One of the developments from the mid-1990s that we alluded to before, that it's not just strings, it's also membranes and three-dimensional blob-like entities. People came up with the idea that perhaps we actually might be living on one of those entities. And it's hard to picture in the actual 3 dimensions, so a 2-dimensional analogy I think is pretty good. If you imagine, for instance, a loaf of bread, maybe I'll just stop right there with a loaf of bread.
We didn't give you breakfast this morning?
Yeah, no,
what was that?
No, so you have this loaf of bread, and imagine that what we have long thought to be the entire universe is just one slice of bread. So a 2-dimensional version of the real 3-dimensional story. And the idea is that there may be other slices, other brains, that we don't see because all of the ways that we access the world, except for gravity, I'll mention in a moment, are kind of trapped on our slice of bread. The strings can freely move along our slice, but they can't get off of it. So photons, that's how we usually see things. The photons can freely move along our slice, but they can't get off. That's why we're unable to see the other dimensions. But these theories also show that since gravity, it turns out, is associated with a snippet of string in which the ends are tied together into a loop, it's not stuck to the brain. The open strings of which we are made are stuck by their endpoints, but when the endpoints come together and yield a little particle of gravity, it can escape, and it can probe into the other dimensions. So the idea is, maybe at the Large Hadron Collider, now imagine there's a collider on this piece of bread. So you've got protons going opposite directions around this collider. They slam into each other, and it's possible, the calculation shows it's possible that some of the debris from the collision would be these graviton particles that could fly off of the piece of bread, and we'd notice that by having a little less energy after the collision on our slice than before, because the gravitons would carry away energy with them. So that's one of the exciting possibilities that might happen at the Large Hadron Collider.
It's an exciting remote possibility. There's also something else that's gotten a lot of press. You may be, because it changes the nature of gravity in these extra dimensions, gravity acts a little bit differently in order for these theories to work, you might be able to create kind of black holes that might do something interesting. And that's fascinated people, but it's also caused a lot of public press and concern. So maybe you want to talk about that for a second.
Yeah, you know, when the Large Hadron Collider was doing its initial runs some months ago, I'm sure it was the case with you too, I got so many phone calls
all the time
to be on this or that program, and I was like, wow, physics is really, you know, its stature has risen, but they only cared about this idea of black holes that might be formed in Geneva and sort of eat up Switzerland, and then, yeah. Which wouldn't be so bad per se, but then if it went on, you know,
actually, you know, it would have helped the whole financial crisis.
I'm telling you, that's right. Or it's a reasonably good metaphor.
Yeah.
But the idea is a serious one.
Yeah.
And scientists in our community have done calculations. I mean, if you create this little black hole, what would happen? Could it eat up the world around it? And the answer is no. And the calculations, number one, they show, based on fairly well-established physics, that these little tiny black holes would disintegrate in a tiny fraction of a second before they could cause, you know, any trouble at all. But even more so, if you don't think that's a convincing argument, these collisions that we can create at the Large Hadron Collider, however powerful they may seem to us, are very weak compared to collisions that are happening in our atmosphere right now. Cosmic ray particles are slamming into our atmosphere with energies far in excess of anything that we'll be able to achieve at the Large Hadron Collider. So little black holes, if they were going to be created in Geneva, would be created there, and if they're created up in space and they're not causing any problems here, well, we should be fine. Some will come back and say, but hang on a second. You create the black hole up there in space, and it has a speed from the incoming particles. Maybe it just rushes through the Earth before it can create any problems. So the final way to answer that is these kinds of collisions also would happen near neutron stars. And neutron stars are sufficiently powerful that they'd hold on to this little tiny black hole. So if black holes eat things up, we should see neutron stars disappearing, and we don't. So the stability of the universe around us pretty much shows us that there's not a problem.
Yeah, and the other example that's been used is the moon, because it doesn't even have an atmosphere.
Yeah,
the fact that the
Right
moon,
into
when
it,
you
yeah.
look up at night, there's a moon, it gives you good confidence that they're probably not there. But
What do you do during new moon, though?
well, that's true.
So half the time you're worried.
Half the
have
time,
yeah.
exactly. You can sleep half the month. The well, let me ask you before we move on to the last thing, because I want to leave time for questions from other people. This idea of extra dimensions, I mean, it is kind of sexy, the idea that we might create them. And I'm excited about one of my students was one of the people who proposed it, as you know, Raman Sundram,
yeah.
when I taught at Yale. And I like to say I was really happy about it because it got him tenure. But I think it's pretty ugly. What do you think?
I don't find those theories from a mathematical standpoint compelling.
Yeah, okay.
So what we were talking about earlier, you're guided by mathematical aesthetic at times, and I don't find that these fit into that.
They don't fit into string theory very easily, do they? I mean, we don't talk about it. I mean, it's just they seem contrived to me, and I just wondered whether you agreed.
I agree with that. The only hesitation I have is, when something's right, we somehow have the ability to go back and modify our aesthetic. That's what I'm unsure about.
And now that's, actually that leads it to the nice segue to the last thing I want to talk about briefly. Because one of the things that I wish more people understood, especially I was down in Texas recently talking at the school board there, that the universe is the way it is, whether we like it or not. and if more people could just get used to that idea, that it's nature that tells us how to behave, not us telling nature, it'd be an interesting thing. So it is absolutely true. Many things have seemed ugly. Black holes seemed ugly. So, but then once you realize that might happen, quantum mechanics, all these things seem weird, and we have to adjust our minds to understand them because, like it or not, that's the way nature works. And so maybe in the last 2 minutes, because I want to leave 6 or 7 minutes at least for questions, both you and I spend a lot of time trying to communicate, and I want. Maybe, and we just did a little TV program the other day talking about that. Maybe you want to elaborate on why you think that's so important.
Well, I think there are a number of reasons that I give when I'm asked questions like that. And sort of depending on the setting, one or another answer I think is most powerful. On the one hand, I truly believe, and I know you do too, that all of the issues and opportunities that we face going forward, the fundamental ones are scientific at their core, right? I mean, the opportunities with stem cells, the challenges with climate change, the possibilities with nanotechnology and human space travel. I mean, all of these things are fundamentally scientific and alternate energy. So you need to have a public that's at least willing to engage with the ideas so that we are making the decision. It's not a decision that's being made on high and basically being presented to us. So I think...
in fact, I would argue that a healthy democracy depends on that, not just in the public, but the legislators as well. If you make decisions in the absence of data, then they're generally not good decisions, as we've learned in the last 8 years.
So I mean, I agree with that fully, but if you were to really ask me why I do what I do, why I take time out of research, to spend time popularizing science, and there is a huge opportunity cost, right?
Yeah,
I used to think that there wasn't,
but there
and
is.
that was when I wasn't married and I had no kids, right? So what I would do is I would do the writing at night, and I do physics during the day, and it simply meant I was watching less television or reading less books or things like that. But that's no longer the case. So there's a real opportunity cost, and the reason in my heart of hearts why I do it is not because of the issue that we just mentioned. It's important, but I do it because when I see a kid open up his or her eyes and say, "Oh my God, this is spectacular," it feels great.
I agree.
And that's why I do it.
No, in fact, and for me, it's precisely comes down to the same thing. It was a gift given to me. I read Isaac Asimov. I read George Gamow. I read Albert Einstein because he used to write popular books too. And for me, that's what turned me on. And so when I write a book and I see a kid, and enough of them are old enough now that some of them say I became a physicist because it's just
exactly.
Okay. Well, enough of that. Let's go to the audience and feel free to come and ask some questions. So I can't. Thank you.
Thank you. Sir.
No, we'll just have to save that. Any? Oh, good. House lights are up, so I can see now. Any questions? I guess, are you at the microphone? Why don't you begin?
Yes. Hello?
You're
Hello?
on. Yeah, we can hear you.
Yes. With the Large Hadron Collider being able to possibly create energy densities that will be in the range that the Higgs boson is predicted to be in, would it be more exciting for you for the Higgs boson to be detected or not detected?
Well, I think it's a great question. Just to amplify it, so one of the reasons for building the Large Hadron Collider was and is to find a particle that we in the community of physicists have assumed exists for the last, I don't know, 25, 30 years, if not longer. But as yet we have not found it. It's the one missing piece of the so-called standard model of particle physics. So, you know, if it is found, it will be kind of bittersweet, I think, because it will show us that these mathematical ideas led to a correct insight about nature, and it will complete one particular chapter in our exploration of the fundamental constituents of matter. On the other hand, it'll be kind of sad, because when you close a chapter and you move on, you know, there's this sense of departure, this sense of, you know, it almost would be more exciting if we don't find it, because there'd be the wonderful challenge to figure out what is going on.
Don't you think for a lot of physicists the biggest nightmare in some sense is that we find it and nothing else?
Yes, for the Large Hadron Collider, absolutely. If you find exactly what you were looking for and nothing else, it's hard for you to use that as a springboard for the next step. It's
As
also,
I say, we don't want to be right. I mean, we need the guidance to tell us whether any of these ideas that are coming up in theoretical physics are actually fruitful.
Yeah, I mean, the biggest nightmare is to find absolutely nothing, because we would find that exciting, but it'd be hard to convince the powers that be.
Hey, we found nothing. Isn't that great? You know. But some of the biggest experiments in the history of physics have found nothing and been very significant, although they weren't funded by the government at the time. Yes.
So I have a third grader and a sixth grader, and they're going through some standardized testing now, but it doesn't include anything on science. I was wondering, as you talk to legislators and others in the government, what is the feedback you're hearing? Because, you know, science is really important, and I really don't see a whole lot of educational emphasis on it.
You want me? Okay. Well, it is a problem. It is a huge problem, I think, and there are two sides to the problem. There are a lot of educators, or at least school board members, who are really afraid that our kids will learn science. I really mean that. Who are afraid that our kids will learn science and somehow lose their faith, and in fact, one of the great things that's happened this year politically is that at a federal level, we now have the present administration has said we believe in scientific integrity and we're going to only appoint people to boards who have the proper credentials. And I've recently argued, although to deaf ears, I think that we should do the same in school boards. That people should actually have some credentials who are going to make the decisions. But the other issue that I know Brian and I have talked about this, and I know Brian feels strongly about it too, is that the other problem is we tend to turn off a lot of kids from science because, for a number of reasons, one of the big problems, at least at the public school level, and it's terrifying to realize, is that in this country, in public schools, most of the middle school science teachers in this country certainly don't have degrees in science. And if you're not comfortable in teaching science, you tend to teach a bunch of facts. But as Brian, and you've talked eloquently about this, I know, it's not the facts that make science interesting. It's the process. It's the excitement. You know, when we're talking about this or string theory or whatever, that's what gets kids excited. And it's kind of sad that we instill this rote facts or require kids to learn these things and not at the same time introduce some of the exciting things that are happening at the forefront. But I think you can only do that if you have some comfort level. If you have some comfort level to depart from the curriculum, or at least included it in the curriculum. And I think that's a problem we have, and that's why the National Academy of Sciences has argued and I firmly believe we should be not only paying teachers more, but recruiting a lot more teachers to teach science who are comfortable with teaching science, and it's only that way that we'll overcome the problem, but it's going to be very hard. I don't know whether you want to add anything else.
Yeah, that captures it well, I think. Yeah.
Okay. Okay, it's all right.
Hi, you described this theory as requiring extra dimensions, and there's also been a radical effort to reconcile quantum and relativity by removing a dimension, specifically the dimension of time. Are any of these timeless models compatible with string theory, and is this an active area of research, or has it kind of been abandoned?
Well, the approach that you're referring to is one that is not as exotic as string theory. It really starts with the basic principles of quantum mechanics and applies them to Einstein's equations as best we can without really introducing anything new. And one of the features that emerges is that time does disappear from the equation, so-called Wheeler-DeWitt equation. And, you know, string theory has enough flexibility with our current understanding that it can embrace these ideas, but in no way would I say that string theory leads us to this particular way of thinking about quantum gravity or the early universe. So I'd say it's really up in the air as to how these quantum theories that involve gravity deal with time. In fact, if you were to ask me what the next major breakthrough would be, I would say it's coming to a firmer understanding of what time is in these theories, where it comes from. Is it fundamental? Is it built up from something more basic? And what does that tell us about the fundamental ingredients of the world? So that, I think, is a big frontier area.
Okay, well, I think actually, given the time, forgive the pun, that's probably a good time to stop. And before I thank you, I just want to say, I know a lot of you, there are books being sold outside. We're not actually having book signings, and we will hope that many of the people here have written books, and we will try and get a number of them signed, pre-signed for you to buy. We meant to do that this morning, but things didn't work. But we want to really break because we want to have some time for people to have a relaxation before the exciting afternoon session. I want to thank all the speakers this morning. You made it so great. But it's true. They were all great. I do want to particularly thank Brian, not only for having the guts to trust coming out to be interviewed by me, but also there are very few people who I think I would feel comfortable enough to know that we could have such a conversation, and it would be, I hope, of interest to you. So thanks a lot, Brian.
Thank you. Thanks.
Okay.